Hello, friends. Welcome to Science Talk. I am your host, Jim Massa. In this video, I wish to go through with you the latest data as of December 2022. This will be an overview. So let's get right to it. First, we'll start out with atmospheric carbon dioxide since 1600. Okay, so obviously start out 1600 over here. And this orange vertical line is 2022. If you look at the scale, it indicates 2025, and of course it goes a little past that. This little horizontal orange line here is you are here. And where is here? Here looks like to be about 412, 415 parts per million according to this. Okay. And of course, this is in parts per million. The overall trend, you'll note, and even starting in around the 1800, 1825 time frame, it starts to exponentiate. So, and of course, we can see the acceleration increasing starting about 1975, thereabouts. And in that time, we've added almost 50 parts per million extra CO2. And it's continuing. The acceleration is continuing. Now, this next graphic starts from 1900, and the global mean CO2 concentration, which is in blue here. So this is just CO2. So again, we get up to about that 412, 415 parts per million. This orangey line is the CO2 equivalent, usually abbreviated as CO2-E. This includes other greenhouse gases, primarily methane and nitrous oxide, N2O. And as you can see, both of these are showing acceleration, exponentiation, but more so with the CO2 equivalent, and it's reaching about looks like 520, 525 parts per million equivalent, which again is going to lead to more warming. And when as we're going through this video here, of course, you can always stop the video at any point during this to further examine the slides at your own discretionary pace. So now here we have 4 graphics. The first graphic, the rising temperature, is based on the baseline from 1991 to 2020. So the most recent 30-year block of time. That's what the atmospheric folks tend to do. They look at 30-year blocks, 1951, 1980, 71 to 2000, 81 to 2010, and so on. So they tend to do that. So basically, if you look at the zero, and these are anomalies, so these are departures from that baseline average. If you look at here, 0, that would be the average. So, yeah, this would be below that average. So what this is telling us is that there has been a lot of warming that even compared to the most recent 30-year block of time, we can still see the overall rising warming trend, and everything, starting from about 2014 or so, the last 8 years, has been warmer than the average of 91 to 2020. That's what this is telling us. These are anomalies, these are departures. And in some cases, almost half a degree warmer just in the last 8 years. Now, the other 3 are simply showing what's going on with the CO2 and the methane and the nitrous oxide. Okay? So again, the oscillatory nature reflects seasonal variation, but the overall trend is unmistakable. It's increasing. Little arrows up here. We see the same thing for methane. Might have been a little flattening out about the turn of the century, and then it kicks back up again. Possible reasons for that would be fracking, rice paddies, more cow flatulence, tooting away, adding methane. And we start having decent data for nitrous oxide again a little after the turn of the century, but the trend is unmistakable. It is increasing. So these are all tied together. You have the rising gas levels, rising temperatures. Changes in annual temperatures. Again, looking at the trend from 90 to 2021. So now it's kind of like a 32 year. Again, Zach Labe, these graphics I'm showing right now, except for the CSIRO one, the second one with the CO2 equivalent, these are all courtesy of Zach Labe. And this is from NASA GISS data. What do we see here when we look at this? These are changes in annual temperature. With the exception of a couple of spots in Antarctica here and here, everywhere on the planet's surface is showing a warming trend. And where do we see the most warming trend? It's about 0.6 degrees C. Okay? And this is, by the way, is per decade. We see it at high latitudes, right up here in the Arctic, and down through the into the Arabian Peninsula as well, Turkey, and Central Europe here, getting into the Eurasian steppes and so forth. But the whole planet is warming. Now, this is for land temperatures. The whole place is warming. Global temperature, 12-month running mean. So you go from like January to December, calculate that. February, so you calculate that, and then you go February to January, March to February, etc., etc. Now the baseline for this here is 81 to 2010. Okay, so 0 would be the average for that 30-year period. Okay? And so when you go down to 1980, up to about, again, the start of the century, with the exception of like maybe 99, parts of 96, and maybe 92, that period from 80 to about 2000 was cooler than the 30-year average for 81 to 2010. And then what happens after that? It's all warm. You can see the drastic warming this century. Doesn't dip down into the blue. Starting in 01, it's just been warming. And this line is the 0.5, again, seasonal variations reflected, but it got as high as up to about, looks like 0.62 or so, warmer than that 30-year baseline average. These are anomalies. Global temperature by year, and it goes back to 1880. Now, the white line, okay, is the annual. Okay. The gray is the 95% confidence interval. Okay. And if you look at this, further back in time you go, you're going to see a larger confidence interval because there's more error, less certainty in the measurement. When you start getting to more recent times here, our instrumentation is pretty damn accurate, so we have less error, so we have a tighter confidence interval. The confidence interval is basically telling us where we would expect to find the actual true value. The bigger the error is, the wider the confidence interval has to be to accommodate such errors. When you get really precise, really accurate measurements, well, the error is really small, so the confidence interval shrinks accordingly. And then this, what is that, burnt orange? Whatever this is, okay, that's the smoothing. What's the overall trend? Zoop, going back up. Right? It's increasing. And we see that the increasing kind of starts about in the 1950s or so and just keeps on going. Now we can even parse this out a little more. Okay, so this is average temperature change. Okay, so again, this is the global mean surface temperature anomalies. Okay, so all this time period was based again on the 1951 to 1980 baseline. Right, so 0 would be the average for that 30-year, and we can see that basically since starting about 1970 or so, things have been warming. So again, this is anomalies on a departure from the 51 to 80 period. And here we have an interesting baseline. We have a baseline of 1850 to 1900. And they tease it apart. So the blue represents the ocean, the white is the global overall, and this red is land. And what we see is that compared to 1850 to the 1900 time period, the land has warmed by about 1.7 C. Overall global is 1.2, the ocean is 1.0. So again, here is the 0 represents the average or 0 departure from that timeline. And we're seeing, when you compare to that timeline, starting about 1920, it's been warmer since. Now look at how much the oceans has warmed. 1 degrees C, 1.0 C. Think of the specific heat content of water. The oceans have been thus far, and they won't be doing this too much longer, the oceans have been saving out bacons. We all know, you've heard me discuss this before, they've absorbed approximately 93% of all the greenhouse gas heat and energy that we have emitted. Right? 93% of all that heat energy, they've absorbed it. And about some 40% or so of the CO2. This would be much higher if the oceans had not absorbed so much energy. That is a lot of energy in the ocean, and that energy is waiting to diffuse, especially as the stratification sets up. That energy will diffuse to the atmosphere, and we're already seeing signs of that. Look at the recent precipitation bombs in California. Look at the meandering, the wild changes in weather patterns, temperature swings, precipitation bombs, etc., etc. So, this is not good. Again, 1.5 above pre-industrial, 1.0 above pre-industrial. Next slide looks at the surface temperature anomalies compared to 1850 to 1900. Okay, but they do a little different parsing. They actually separate it by hemisphere. So in the previous slide, this is north and southern hemisphere. This is all terrestrial lands, no matter where it's found. Here, they separated by the northern hemisphere and the southern hemisphere. And then globally, but excluding the polar. No polar land, okay? So all this is for land. What do we see here? Again, it's based on 1850 to 1900. And we see that we are pushing 2 degrees above pre-industrial in the northern hemisphere. And now, since for planet Earth in its current configuration, most of the land mass is concentrated in the northern hemisphere, when you hear that, oh, we can keep it under 1.5, well, these values would kind of tell you that's moot. That's not going to be realistic. So, and I've actually seen, when you factor in all of the stuff here, I've actually seen estimates of basically 1.5 to 1.65. But this just shows you, and again, the trend's unmistakable. It just keeps increasing. Just keeps increasing. Okay. Now we're going to look at sea surface temperature anomalies. Okay. So the anomaly is going to be compared to 79 to 2000. Okay. So 0 is and these are departures from this average. The 0, of course, is no departure. So if you look, for example, at this point right here, which is, it looks like about 1988 or so, there was the sea surface temperature was no departure from this 30-year average. And it's looking at 30 to 60 degrees north latitude. I like the 0 degrees east to 360 degrees east. That means just go around the whole planet. You could substitute a W here for west longitude, whatever. But the rate of global warming has doubled in the past decades. Okay? Just look at what starts for the oceans, starting about 95. Whomp, it's going up. This is just sea surface temperature anomaly. So it has warmed up by basically 1 degree C, which is in agreement. Right here's 1.022, which is in agreement to the previous slide here, right? But also, if you remember my ocean heat content videos, what did I say that I think happened in about 1995, 96 or so? That's when the planet went past an irreversible tipping point as a whole. And that's because of the ocean heat content. No longer being able to sequester heat to depth along with the CO2. Now the heat starts accumulating in the first 2,000 meters, especially in the upper 700 meters. And we get this. And all that, and it's going to lead to stratification. But by not being able to sequester that heat, this is helping to fuel the atmospheric increase in temperatures. And now the Arctic is warming. So basically, this is the Arctic. Right? We're looking at 10-year chunks, 82 to 91, 92 to 01, 02 to 11, and 12 to 21. And they do the same thing for the ice. So let's look at the Arctic. These are temperature anomalies. Again, departures, and the baseline is 51 to 80. So 1951 to 1980, that's the baseline. And we can see it's starting to warm, and then it really starts warming. And then look what's going on in the last decade almost. Really, really warming. And look at this. This is pretty much over the Barents Sea. And you can see that the Eurasian side of the Arctic is where it's getting hit with the warming. But the whole Arctic is warming. Here's Alaska, by the way. Okay. So right there in the Chukchi Sea is pretty warm. It's warming. And if you look at the scaling here, we're talking 4 to 5 C. That's significant. So down here with the sea ice thinning, we see they look at the sea ice thickness in meters each year. And what this indicates to us, so this bright white stuff here, that's about 5-6 meters thick. Okay, getting to about 2.5, 3.5 or so meters thick over here, and then we get into the thin stuff here. But what do we see happening overall? We see the ice thickness thinning down. Now, what this also is telling us is this relates to volume. The thicker ice usually reflects the older sea ice. the multi-year sea ice. So the multi-year sea ice, as we can clearly see looking across here, we're losing it. In fact, based on the most recent that we have, is probably about 2 meters thick. We don't see any more to 4, 5, 6 meter thick ice anymore. It's disappearing. It's thinning, which will then facilitate the further loss and total loss of ice, sea ice. So here's showing the Arctic sea ice volume in November since 1901. And basically, the total volume for 2022 is at about 10,000 cubic kilometers. So it has gone from a height of about 24,000 cubic kilometers all the way down to about 10. So they looked at a couple biomass data sets with some updates. This is ice volume. Sea ice extent is even less. The area is really dropping. And now we can take a look at land glaciers, alpine, continental, right? And it's just diving. It has dropped. Okay, so this is the meter water equivalent. And it's down. It's gone from, it's just down minus 25 or so. Just losing all that ice that's on the land. And an alpine glacier with the slow melt that typically would happen, that'll, meets out nicely for human consumption, irrigation, so on. Well, now you're just losing it, and what's left? So we're setting up a lot of drought conditions is what's happening. So the previous slide I showed you, all courtesy of Zach Labe, except for that one there with the CO2 equivalent and the CO2, which were CSIRO, and this slide by Leon Simons. Okay, now we're going to take a peek at Alaska. So we're going to look at Utqiagvik, formerly known as Barrow, but it's now the name change is official. It's Utqiagvik. The average November temperature of 13.9 F with about minus 10.1 C is tied for the sixth highest in the past 103 years. 5 of the 10 mildest Novembers have occurred since 2016. Okay, so 16 to 22, that's 7 years inclusive, the two endpoints there. 5 of those 7 years have been 5 of the 10 mildest Novembers. The phenomenal trend since 1990, strongly driven by sea ice loss. If there's no sea ice and you have all that warmth coming in through Bering, that heat gets diffused, it fluxes to the atmosphere, and it makes the situation milder. And as we'll see later, increases precipitation amounts. So, a whole bunch of next bunch of slides is going to be courtesy of Rick Toman. He's a really cool guy, very knowledgeable. So, of course, ACAP, Alaska Center for Climate Assessment and Policy. So the red dots are the 10 warmest, the 10 coldest are the blue dots, and the grays is just everything else. And then this green line is the estimated average. As you can see, it's pretty much a buckshot up until about 1990 or so. It's pretty much flat line, no real deviation of the average, and then all of a sudden, it starts going up. And 1, 2, 3, 4, 5. There's those 5 of those warmers year that I mentioned here. So there it is. There's your 5 warmest years. A definite trend increasing temperatures. The total change in December average temperature. Okay, so there's Fairbanks, Fort Yukon, Dead Horse is Utqiagvik. That's Point Utqiagvik right up there. So you can see the coastline of Alaska here, over to Nome, good old Kotzebue, and so on. Alaska Peninsula on Alaska. Notice where it's really hot, and this is total change. Total change in this time period, 72 to 2021. But it's really, really hot over the Chukchi Sea and the Bering Sea. So that means it's warmed that much, it's giving off that much heat energy, and it's keeping things warmer in December. To the point that in December 2021, we had freezing rain in Fairbanks. Let me tell you, that was not fun. It's treacherous to go driving. But overall, you can see how pretty much, exception of some certain areas here and here where stayed about the same, no real warming, pretty much the entire state of Alaska warmed up. But the warming is most noticeable on the North Slope because it's close to the ocean that now is staying open longer. It freezes up later, melts earlier. So it's going to really affect the temperatures. Change in the precipitation for November. Okay, so how many percentage this is getting more precipitation? This is getting less precipitation. Well, pretty much everywhere you see, maybe 0 to 10% increase in precipitation, but everywhere you see, there's been a massive amount of precipitation, and again, especially over in the Chukchi and the North Slope. So a lot of rain and snow on the ocean because the ice isn't forming, the heat is fluxing to the atmosphere, it cools, it condenses, and it returns in precipitation form. Percent change, okay? So this is just percent change in the average precipitation. Now we want to look at the percent change in snow. Greater than 70% increase for the same regions. So where we see, the, tan color, we actually had a decrease in snow. So if you go down to southeast Alaska, they see, and southeast Alaska is pretty much, it's almost like temperate rainforest climate. And they're seeing a decrease in snowfall. So either they're getting less snow, well, it means they're getting less snow, but it means that they're getting less precipitation, or instead of getting snow, they're getting rain, which is not fun. So we can see the overall changing characteristics take place over Alaska and into the Chukchi Sea, all driven by the loss of sea ice, driven by warming oceans coming in through the Bering Strait. So these analyses just show you is based on the ERA5 reanalysis data from the ECMWF Copernicus and use the most current version of the reanalysis available as of this writing. That was a statement by Rick Toman, and he now has a blog, Alaska and Arctic Climate. I highly recommend you go subscribe to that. He actually breaks down in detail the analyses used and why certain analyses are preferable over others. And again, those previous slides were his work. Now we get to the ocean heat content. And what do we have here? No surprise, it's warming. It's absorbing more heat. And again, this is the total content in 10 to the 22 joules. 10 to the 21 will be zettajoules. So, but this is just total 10 to the 22 joules. And the baseline is 51 to 80. So 0 would be, the baseline for that. And what again we see starting in about 1991 or so is just increasing. So they have a pentatal average. That means the 5-year running average. That's why it stops here at about 2017, 2018 or so. This didn't get darkened enough, but the yearly average through 2021, that's this black line here. And then the 3-month average is this red line here. So they did a little more because we have better data to there, so they're able to do a little more refined analyses, and again, reflecting seasonal changes here. But overall, the ocean's absorbing heat energy and getting warmer, and there's more of that energy in there. And it's looking from 0 to 2,000 meters down. So this would be integrating over the entire water column. Now, let's look at it for the first 700 meters. Okay. And again, 51 to 80 baseline. The same thing, the blue line is the pentatal, the 5-year running average. Then this is the yearly average and the 3-month average. So the same situation as here. But now we're able to tease out and look at the upper 700 meters and really warming up. So if we were to look at these values here, if we take the black line here and go across, that looks like it's about 18 times 10 to the 22 joules. Where if we look overall, okay, look at up here, that looks like it's about 27 times 10 to the 22 joules, according to this information here. So you're going to say, well, why is it less? Well, because we're only looking at the upper 700 meters. So the difference would be the other, pull this out, the other 1,300 meters from 7 to 2,000. But the oceans keeps absorbing more and more of it. That's the point. The change in the global ocean content since 55. Okay, so now we're just looking at 1955. So where these were looking at the baseline comparison, now we're just calculating overall change in the key content. Again, 0 to 2,000 meters down. So this is now anomalies, so it's not total. Again, 10 times 22 joules. It's annual. And what they have here is this bright blue on the measurements. The blue shading is 95% confidence level. Okay. And the red dashed line is a 30-year lowest fit. Now, lowest, not lowest, so it's WOLESS, not EST. So it's not saying a minimum value. It's a type of regression analysis. And we can see they fit it through here. And I'm going to say something about this red dashed line in a moment. But I want to point out to you again that you notice that the confidence interval shrinks as we get later and later because our ability to measure becomes better and better with lower and lower error. Therefore, lower and lower error increases the accuracy and precision. Therefore, we have a smaller confidence interval. Now look at the shape of this red dash line. Does it appear to be linear? Of course not. This is curved. Now, it could be exponential. It could be polynomial. for example, quadratic, but it's not linear. Now we do the same thing, but looking at the 0 to 700 meter layer. Okay, so you notice what I'm doing here is I'm showing, overall, 0 to 2,000 meters. Then I break it down to 700 meters. Okay, compares to the baseline. And now we're looking at the change. So the anomalies, again, 0 to 2,000 meters, and then again, 0 to 700 meters. Looking at the changes here. And you can see that the change is almost 30 times 10 to the 22 joules. Overall, it's about 45 times 10 to the 22 joules. So that value that you might remember from my ocean heat content video when I was saying, how many zettajoules was in the ocean, that there was a boatload of it. That's the anomaly. That's the change there. So what we see here is the same thing. And again, we have that red dashed line. That is not a linear function. And now look at the rising ocean waters. Okay, so the global mean sea level anomalies measured in millimeters. Okay, so the baseline is just from 1996 to 2016. That's like a 20-year period. Okay. So they start this in 93, and we can see a couple little dips here and there. But overall, sea level is rising. Now, when you look at this red line up here and you carry that across, that looks like it's about 67 millimeters or so. 67 millimeters is 6.7 centimeters. Well, 5 centimeters is 2 inches. This is almost like 2-3 inch increase in sea level rise. Overall for the planet, for the globe, there's going to be some areas where it's going to be higher due to westward intensification of the gyres. So basically you'll see a higher sea level rise on the western margins of the oceans, off the eastern side of the continents, so forth. But it's rising. In my ocean heat content updated video, I showed you how this was all accelerating. That the rate of the rise in sea level was in itself accelerating. Now I want to point out something to you down here at the bottom. The red dashed line is a quadratic fit. In other words, this is a polynomial of degree 2. Think of like y equals x squared. All right, keep that in mind. It's a quadratic fit. These are probably might also be quadratic fits as well. Ocean heat content is increasing non-linearly. Sea level rises are increasing non-linearly. So again, the previous slides are courtesy of Zach Labe. And now we're going to look at slides from Cheng. So he looks at the global ocean heat content time series relative to an 0615 baseline. So he's really tightening it down. So that average would be here. And we can see that in the last 7 years or so, about 10 times 10 to the 22, maybe looks like maybe 12 or so times 10 to the 22 joules has been added above the baseline. Notice the wide confidence intervals, and then the confidence intervals get smaller as we get to present day, thanks to improved ways to measure. Now, the next two graphs are going to look very similar, and you're going to say, but what's the difference? Aren't you showing the same thing twice? And the answer is no. Okay? Let's look at this one first. This is looking at the month of September in 2022. Looking at 0 to 2,000 meter ocean heat content anomaly field, looking at a 1 degree by 1 degree grid. It's 1 degree latitude, 1 degree longitude, compared to an 81 to 2010 baseline, and the units are in joules. Okay? This is anomaly compared to that 30-year baseline. As you can see, the scale goes from what? -5 up to +5 or more. And what do we see? Well, we see that it's really warm in the Arctic Ocean. Right? We see that. We see that it's about 1 degree to maybe 2 degree, and then when you get over to the Barents Sea, it's more than 5 degrees. We see that it's warm in the North Pacific. We see that it's warm in the Western Equatorial Pacific, warm in the South Pacific, and the Southern Ocean is warm. South Atlantic is warm. And even Western North Atlantic Ocean is warm. We see that. So what's the next one going to show us? The next one shows a more refined difference. So able to tease out more difference here. So the scale just simply goes from -1 to 1, and we can see there's a lot of heat in the North Pacific. Remember that heat blob I showed you? And there's a lot of heat in the South Pacific, a lot of heat in the Western Equatorial Pacific, and in the South Atlantic, as well as the Southern Ocean. And even in the North Atlantic, we're seeing, warming of at least 0.4, it's not a warming, but an increase of 0.4 times 10 to the 22 joules. So the difference between these two slides is that this is showing an overall warming, and then this kind of shows a little more detail, kind of parsing it out a bit more. I want to point out what's happening in the Eastern Equatorial Pacific. Notice with the larger scale, doesn't look like much is happening in the Eastern Pacific. But when we get the finer scale, there's the La Nina signal. You can see it right there. And a bit cool, almost 1 degree. It's a bit cool as far as the joules go. So we can see the La Nina signal here. So that's what he's doing. He's going larger scale and then like zooming in kind of deal to show you some fine detail. So feel free to go back and forth between these to examine these graphics further. So those previous slides are courtesy of Lijiang Chen. He's kind of like the leading guru on the ocean heat content. Okay, now we're going to look at Earth's energy imbalance, EEI. So NASA's series radiative flux data for 2021 has come available. The annual Earth's energy imbalance was positive 1.52 watts per square meter. The energy equivalent to 1 million Hiroshima-sized atomic bombs every day. Now look at what he's saying here. The rate of global warming has tripled in the last 20 years. Tripled. Ocean heat content data shows a doubling for the longer time frame from 1960 to 2015 to after 2010. keep in mind, specific heat of water, ocean heat content is doubling, ocean global warming is tripling. And now it's said that the Arctic is warming 4 times faster than the rest of the planet, 3 to 4 times, maybe even 5 times in certain locations, like what I showed you around the Barents Sea. So here's the Earth energy imbalance. Again, seasonal differences being reflected. Okay, watts per square meter. It goes from 0 to 1.6, and you can see that it is increasing, and the slope of this line, this fitted line, is this value. It's increasing at that rate. The flux data just came available for the 12-month, so for January 2022, from February to January means a record 1.6 watts per square meter. Absorbed solar radiation increased more in the past 20 years than outgoing long-wave radiation, resulting in an increase in Earth's energy imbalance, the rate at which the world warms. In other words, the absorption rate is more than the outgoing rate. So in other words, if the amount of heat absorbed is the same as the amount of heat lost to space, then your energy imbalance is 0. There is none. But if you are absorbing more heat than what's being lost to space, you're going to have an imbalance. You're going to have a warming. And this is what we're seeing. So let's take a look at it. Okay. So this is a 12-month running mean. So we have the outgoing long-wave radiation, OLR, that's in this red here. You can see what it's doing. We have the net TOA radiation. TOA means top of atmosphere radiation. Okay. So what happens at the top of the atmosphere? Again, we see the patterns here. And then look at the absorbed radiation. And what they've done in all these 3 cases here, they fit the best line. Now, if you look at the top of the atmosphere radiation and the outgoing long-wave radiation, remember, solar comes in on the UV side, right, where sunscreen protection, but after it's reflected and absorbed, it goes out on the infrared side of things. If you look at the slope for the top of the atmosphere radiation and the outgoing radiation, they're almost the same. Not exactly the same, but they're almost the same. But look at the absorbed. You see how that is a higher slope. You can see how it is diverging, right? Whether it's compared to the TOA or the outgoing. But let's compare it more germane, is compare the absorbed to the outgoing. You can see how it is diverging. That divergence, that's your Earth energy imbalance. I did a video on that. You might want to go check that out. There it is. That is telling us we're absorbing more heat, trapping more heat than what's escaping to space. And this is looking from starting in 2000. And this particular one runs out right us up to 2022. So we see that the imbalance is growing. Now, this gentleman here, Loeb, in 2021, he expected the rate of heat uptake would decrease if the PDO, the Pacific Decadal Oscillation, were to reverse. But the PDO has been negative since 2020, and the net TOA radiation has only increased. This makes the record of imbalance of 1.6 watts per square meter even more significant. In other words, what was expected was that if the PDO is negative, that the rate of heat uptake decreases. If the PDO is positive, then the rate of heat increases. And there's a link to the site, to the study, if you wish to look at it. And again, Leon Simons provided these graphics here. So what is he talking about? This is the conclusion from this Lowe report. The excellent agreement between satellite and in situ trends in EEI obtained in the study demonstrates the benefits of having independent satellite TOA radiation observation and ocean heat content measurements for tracking changes in EEI. That both produce nearly identical results provides confidence that the trend toward an increased EEI reported here is robust. In other words, it's real, it's happening, and going on, since it is unlikely to be due to artifacts in both observing systems. The positive trend in EEI is a result of combined changes in clouds, water vapor, trace gases, surface albedo, and aerosols, which exceed a negative contribution from increasing global mean temperatures. So in other words, if you have less clouds, you're going to absorb more heat. And if you have, but then water vapor and atmospheric gases, greenhouse gases can hold heat. Surface albedo, do we have snow or not? The snow reflects, no dark surfaces absorb. Aerosols, we know aerosols cool things down. But of course, water vapor in clouds is a double-edged sword. The bottom of clouds traps heat, the top reflects heat. So is you going to have more heat reflected to space and more heat retained? That is a very difficult aspect to ascertain. At a global scale, the aerosol contribution is small compared to other contributions. This may be because only aerosol direct radiative effects are explicitly calculated as part of the aerosol contribution. Aerosol indirect effects are implicitly included as part of the cloud contribution in EEI. So they're making the assumption that cloud is negative, in other words, would reduce the EEI. Quantifying aerosol indirect effect would require model simulation to be run without aerosol cloud interaction. Because EEI is such a fundamental property of the climate system, the implications of an increasing EEI trend are far-reaching. A positive EEI is manifested as symptoms such as global temperature rise, increased ocean warming, sea level rise, intensification of the hydrological cycle. We can therefore expect even greater changes in climate in the coming decades if internal variability associated with the PDO remains the same. If the PDO were to reverse in the future, that reversal would likely act to decrease the rate of heat uptake. Further modeling studies are needed to fully understand the increasing trend. Well, what's he talking about here? Okay. The blue values are when the PDO is in the negative phase. The red values are when in the positive phase. Increasing redness is more positive. Increasing blueness or darkness blue is more negative. Now, review. If PDO is negative, rate of heat uptake decreases. If it's positive, rate of heat increases. Okay, so for the graphic, the data I'm going to show you, PDO being positive is red. PDO being negative is blue. Positive heat increases. As we can see from 2014 to 2019, it was positive. Right? It was positive starting second half of 02 through about middle of 06. It was positive. So we would expect the rate of heat increase we expect the rate of heat to increase through here. We would expect to see it slowing down, but what they're finding is that it's not quite happening as expected. And I submit it's due to the ocean heat content and thermal inertia, which includes ocean heat fluxing to the atmosphere, which is why it's able to mask or eliminate an expected heat decrease. But we're still Even with the PDO being negative, we still see the growing disparity, the increasing Earth energy imbalance. Now, I did a video on the Pacific Decadal Oscillation. You may want to check that out as to what the different phases are and how that affects the situation in the Pacific. And for that matter, over North America and Eastern Eurasia. And here's the data set right here. That's the link for that, the URL for that. Okay, annual global surface temperature anomalies of the Earth, land, and ocean from 1950 to 1921. Anomalies are with respect to the 61 to 90 standard averaging period. Major tropical volcanic eruptions are associated with cooler global temperatures. Strong ENSO years see a response in annual global temperatures such that the year following the start year of an ENSO event is typically warmer than usual with an El Nino and cooler with a La Nina. This is seen in 2016, the warmest year in this data set, following the start year of the 2015-2016 El Nino. Neutral years are those with no moderate or strong El Nino or La Nina events, and based on World Meteorological Organization data. That's what this, so this was a description. Oops. This was a description for this graphic. Okay, so the yellow bars are showing volcanoes, orange are El Ninos, dark blue is La Nina, light blue, neutral, weak ENSO years. So temperature anomalies in degrees C. Global temperature scores vary from year to year. Increase in surface temperature mean a La Nina year. Increasing surface temperatures mean a La Nina year now is warmer than an El Nino year in the 1980s. And right now, we're still in a La Nina situation. It is expected that maybe we'll be in neutral by the summer, perhaps moving into El Nino by autumn of this year. That remains to be seen. But those are the projections and seeing that we will come out of the La Nina, but whether it will be neutral or a weaker kind of El Nino remains to be seen. But when we started from 1950 to 2010, okay, that's zero. Right? Zero. Let's go back and review. We're looking at 1950 to 2021, and they're looking at 61 to 90 as the standard averaging period. So, wrong way. So basically, the zero line is the 1961 to 1990 average period. And we're going from 50 to 2021. And as you can see here, all the temperature anomalies are positive. And here's 2016, the warmest year. And even now, okay, this is a weak ENSO year or neutral. It's still warm. And this is a strong La Nina, and a strong La Nina is still warmer than an El Nino in the 80s. Look at that. It's warmer than an El Nino of 2010 and 1998 and 03. And this is the La Nina we are currently in. Imagine we go to El Nino with all the data we have, all the warming surface temperatures, all the heat content. This could spike like you wouldn't believe. And then you're going to have havoc unleashed. This is incredible. Look at that. This is La Nina. And it's warmer than these guys here. Okay. I want to kind of, show what the humans are doing as well. So this is for cod. This is the fish landing in tons. So it goes from 0 to 900,000 tons. It starts in 1850. goes up to about 2005 or so. So this is the annual catch of North Atlantic cod, showing overharvesting. Hello, right here in the 60s and 70s, and then bang, the collapse. Right, starting in like about the mid 1990s, zero. Caught them all. We'd sent it commercially extinct. And looks like there's some catches here, but no. Basically, we killed the cod industry. I remember in the mid 90s, right about this time here, the fishermen in Newfoundland were told that, okay, no more fishing. One fisherman stood up at the meeting and said, "States, boys, we caught them all." And they sure did. Here's your major overharvesting. Did not allow enough of the cohorts to escape, to spawn. Your class strength weakened, and bang, just collapsed. We see was the things. So what's this uptake? What's this uptick going on? This is when we start seeing improvements in like sonar gear, better mesh, and just longer CPUE, what's called catch per unit effort. And then that's when they just basically finished them off, and then bang, it just dropped. Human influence has warmed the climate at a rate unprecedented in at least the last 2,000 years. Changes in global surface temperature relative to 1850 to 1900. And by the way, when I was showing you the slides earlier with Zach Labe, he's going back to 1850. I contacted him and I asked him if he had data going back to 1750, because that's generally, like for example, NOAA, when they calculate their AGGI, annual greenhouse gas index, they use 1750 as the baseline, and as folks like PIK, in Potsdam, Germany, they use 1750 for their analyses instead of 1850, 1880, 1920, like the IPCC always moving around. He said that unfortunately he didn't, otherwise he would have done those analyses. I have gotten pushback before in the past where, criticizing this constant changing the baseline. And people, well, we didn't really have the data, this, that, and the other thing. And it's like, well, I beg to differ. We actually have data that goes back to the 1600s, in all honesty, because what was happening on starting in the 1400s and 1500, all those centuries of all the wooden ships, right? England, France, Spain, Portugal, the Dutch, right? All sailing the seas. Of course, they were engaging in certain practices that they shouldn't have. That's another discussion. But one of the duties of the captain was to collect data. Because yes, they knew how to find latitude. They wanted to find longitude, but they wanted to collect data. So what was some of the data they were collecting? Air temperature, sea temperature, wind speed and direction, current speed and direction. And they were mapping this all out. Oh, that's what they were doing. Now, unfortunately, it's not like, you have, captain's log. Okay, Mr. Smith was an idiot. He got 10 lashes or something like that. First mate Jones, decided to do this, that, and the other thing. And then a section at the end of the entry. And here is the data. No, it'd be like Mr. Smith was an idiot. He got 10 lashes. Oh, temperature was this. Mr. Jones decided to do this. Oh, current was this. So it was all interspersed there. So to get the data, you actually have to pour through and read through the logbooks to do that. And we actually have oceanographic historians who this is what they do. So they have this data, and they've been compiling it, and it allows us to see the changes over time, over the centuries. Now, of course, back then the equipment, of course, is nowhere near as precise as today, but it still gives us an idea of what's going on. So in this first one here, this left side here, we see change in global surface temperature decadal average as reconstructed, that's using proxy data, from year 1 to 2000, and then observed from 1850 to 2020. Okay, here's the observed, so this black stuff here. And, right, big confidence intervals here because of, the uncertainties, the errors. Warming is unprecedented in more than 2,000 years. Wah, right there. Here it is. There it is. And then the change in global surface temperature as observed and simulated using human and natural versus only natural factors. Both looking from this observed period, 1850 to 2020. So what they're saying here is, if you follow these graphs here, these lines here, this one here, the blue with the confidence interval shading, is just looking at natural only, solar, volcanic, what have you. In other words, teasing the natural variability, the natural signal out, just looking at that, and you can see it's pretty much level, pretty much consistent. It's when you throw in human activity that, we get this massive increase. Tease out the human activity, and the climate would have stayed steady. Human activity is warming the planet. That's the takeaway from this graphic. And now we show how we're further really changing the planet and messing things up. Distribution of mammals on Earth. Now, this is terrestrial mammals. It does not include cetaceans or, for that matter, pinnipeds, really, because pinnipeds spend a lot of time on land to kind of bask, digest, have their pups, but they spend a lot of time in the water. But looking at wild mammals, mammalian biomass shown for the year 2015. Wild mammals, only 4% of all the total global mammalian biomass. That's 2015. It's even less today. Humans, about 34% of all global mammalian biomass. It's even more so today, right? We just passed 8 billion. Livestock and pets, overall 62%. They break it down, 35% cattle, 5% buffalo. I'm surprised that horse is only 2%. Then you got goats, sheep, pigs, camels, asses, and then pets. So when you add this up, it adds up to 100. 34 and 62 is 96 plus 4 is 100. But humans and their livestock accounts for 96% of all mammalian biomass as of the year 2015. It's more so now. Right, 1850 baseline. Population overshoot has led to the devastation of biodiversity, increased habitat loss, leading to extinction, monoculture, fields of growing one crop, loss of albedo from disappearing Arctic sea ice, permafrost thaw, land-based glacial melt, black carbon particulate on ice snow, which changes the albedo, blackened wildfire areas. So the habitat loss is causing mammals to die off, causing extinction, along not just mammals, but all the other organisms. Flora, fauna, all. Humans are causing this current mass extinction. And population overshoot. Okay, 8 billion people is too many. It's just not enough resources to sustain this. You're not going to be able to grow enough food. Right? I did a video on this. Carrying capacity is 100 to 600 million people. That's it. In order to be able to replenish resources that are extracted and harvested. 8 billion, you keep extracting, you keep harvesting, you're not replacing it fast enough, you're going to run out. You can't have exponential growth on a planet with finite resources. You just can't. Not sustainable. I'm seeing reports of how there's going to be mass starvation this year. And we talked about the availability of clean water. Okay, so that's kind of an update of where we're at the end of 2022. Overall, we just see things accelerating. Warmer and warmer conditions, less and less ice, higher sea levels, and everything else that implies. Hope you found this informative. Talk to you soon.